Well, thank you, everybody. Today I'm joined by my co-author, Baxter Miyake, and we'll be discussing our recent groundwater monitoring and remediation article titled Lightning in a Bottle, Electrochemical Oxidation and Plasma for PFAS Destruction. Well, thank you, Baxter. If you wouldn't mind starting off with just an introduction of yourself, a little bit of your background and what you do for Arcadis.
Yeah, thank you, Craig. So I'm a licensed engineer in environmental engineering here at Arcadis. I've been here since about 2019, about 7 years now, with a focus on PFAS treatment specifically. So my PFAS experience is across different industries, federal, municipal, commercial, academia, really focusing on PFAS treatment and destruction technologies here at Arcadis.
Excellent. Well, let's jump right in. Let's start with the reason we chose these two technologies as a focus area, and then we'll get into the details of the technology.
Sounds good. So the electrochemical oxidation and plasma technologies that we selected for this article have really emerged in the last few years. They have pretty high technology readiness levels now. Electrochemical oxidation has a TRL of 8 in some recent publications, and plasma has anywhere from a 7 to 9. So really has shown in the last year or two that these technologies are really ready for commercial applications and are really validated to use in the industry now.
Excellent. So electrochemical oxidation, what is it? Why does it work for PFAS?
Good question. So at its core, the electrochemical oxidation mechanism, it's a direct electron transfer, basically at the surface of an anode or an electrode that generates reactive radicals within the cell. So this direct current between the two different electrodes really drives the process for PFAS destruction. Really, this technology has been around for several years now. I think it goes back to 2008 when there was a first proof of concept in the lab study. Recently, in the last couple of years, there's been a number of publications demonstrating PFAS destruction in this technology in different matrices across the industry.
Excellent. So how would you describe its key advantages and also let's touch on some of the limitations?
Yeah, definitely. So the key advantage of electrochemical oxidation certainly is the destruction of the PFAS molecule. You're not shifting it from one media to the other. So for that reason, it's really good on concentrates. And what I mean by concentrates is foamates from foam fractionation or membrane reject from maybe reverse osmosis or nanofiltration systems. So any technology that might be concentrating PFAS down into a lower volume, higher concentrated waste is really good for electrochemical oxidation, as well as plasma, which we'll talk about in a minute. Some of the concerns or maybe limitations, I'll say, with this technology is you can certainly have some longer residence times. We've seen them upwards of hours, maybe even greater than 6 hours or 12 hours, sort of in a batch mode. So you might be throughput limited on some of these systems. Certainly some secondary water quality concerns with electrochemical oxidation, maybe with short chain PFAS generation or geochemical constituents in the water that might impact the performance. And certainly with electrochem, specifically the anode durability. So there's been a lot of research in different sorts of anodes. There's probably over a dozen different vendors using different kinds of anodes to really optimize the process and understand the long-term impact and even resilience of these anodes and how frequently they need to be replaced.
Excellent. So what are the current applications that have been demonstrated and how might that change in the future with EO?
Yeah, EO has certainly been demonstrated on different matrices with PFAS impacts, anything from groundwater to wastewaters, certainly on concentrates, like I mentioned before. And really what we're seeing is a lot of kind of on-site applications where there's been a number of pilot demonstrations, even some industrial clients purchasing EO units to operate on their sites themselves. And I think more of what we're going to see in the future, some kind of movement towards maybe a centralized approach, either within a certain industry's work or maybe even by some other waste management clients that might be purchasing some of these units to have at a centralized facility where you can eventually ship these concentrates and waste to destroy at one location.
Well, let's pivot to plasma now. What is it? Why does it work for PFAS?
Yeah, plasma is certainly an interesting one. When you hear the word plasma, you probably think of this, sci-fi type of material. And what I usually like to start with, right, is plasma sort of the fourth state of matter. It's found very commonly in nature. So everything from lightning to the sun to even our neon lights and fluorescent lights tubing has plasma. So at its core, plasma really is just electrically charged particles, and plasma occurs when a gas becomes ionized, meaning that its atoms or molecules lose or gain electrons. So it's a pretty cool fourth state of matter that's now been applied for PFAS destruction in water treatment technology as well.
Excellent. What is the mechanism by which PFAS is destroyed through plasma?
Great question. So plasma-based water treatment uses electricity to convert water into a mixture of these highly reactive species, also known as plasma, and those rapidly and typically non-selectively will degrade the PFAS and defluorinate it down into its minimal byproducts.
That's really exciting. Likewise, what are some of the distinctive advantages and some of the limitations of the technology so far?
Yeah, great question. So plasma, certainly one of the first things people might think of is that it requires a large amount of energy as a negative. And what's really interesting is that there's different types of plasma treatment technologies out there. So there's both thermal plasma and non-thermal plasma. So depending on the type of plasma you're talking about, it can have a high energy impact. But certainly for PFAS destruction, the focus has been on these non-thermal plasma applications, where the electricity energy requirements are actually similar to something like a microwave oven, which can actually be a lot more energy efficient when you're thinking about PFAS destruction technologies. Some of the other possible concerns, or maybe I'll say disadvantages of plasma, it can affect some water quality parameters like pH, so you might need some additional pre-treatment or post-treatments. And even, I guess, in the industry, its actual mechanism of destruction is maybe not as well understood as some of our other technologies. But with the demonstrations that have been done and the data that we're seeing, it is very effective at destroying PFAS, 99% plus DREs that we're seeing on some of these studies and literature.
So Baxter, as you think about these two technologies, how would you compare them? They're two exciting tools. How would you compare them as they currently are demonstrated? And where do you see them evolving to? And how do they fit into the growing and future markets?
A lot to unpack there in that question. That's a good one. So definitely electrochemical oxidation and plasma. We've included them both in this article because they are comparable destruction technologies. As mentioned at the beginning, they have very similar TRLs. We're seeing them commercially readily available for our clients, and we're seeing very high PFAS destruction efficiencies and proven performance on both of these. Where the differences really are going to come down to are ultimately cost implications, both capital but also long-term O&M costs. So what are the costs going to be for replacing those anodes down the line? What are the costs going to be for maybe using any gases in the plasma process down the line? And looking at these holistically, at a longer term operation on these different sites. In the industry, I'm also most excited about seeing both of these technologies actually included in some vendor packages that are also offering foam fractionation. So it's also an indication that some of the foam fractionation concentration vendors see value in both of these technologies, both EO and non-thermal plasma, and they've actually incorporated them into the back end of their foam fractionation systems. There's about, I'd say, 5 or 6 vendors now doing that and offering a packaged approach where the foamate is actually destroyed all within the same unit, either through EO or plasma. So it's exciting to see these technologies not only as standalone, but being coupled in the treatment train approach with our concentration technologies in the industry as well.
Baxter, when we think about the various PFAS wastes that need to be destroyed, how do these technologies fit into that PFAS waste market that's current and in the future?
So both of these technologies, electrochemical oxidation and plasma, and non-thermal plasma specifically, are really geared towards our water-based matrices and concentrates. So anything liquid, anything that flows. There are a number of other technologies for the solids and biosolids even, where plasma might be used, for example, but these non-thermal plasma and EO options that we're talking about in the article today are really focused on kind of the liquid waste streams.
Baxter, this has been a great conversation, and it's very exciting to see the evolution and the maturation of these technologies. Thank you for your time.
Thank you.